and how there's differences in nuclear genome versus the mitochondrial genome, the arrangement of genes in yeast compared to that of humans, and comment on the term of junk DNA. So specifically, when we look at the differences between the nuclear genome and mitochondrial genome, in this image you'll see that in the nuclear DNA, you're going to see that there's more base pairs, it's linear, it's open-ended, and it basically contains the genetic makeup of a human being, containing more than 20,000 base pairs. But in mitochondrial DNA, you can see here that it's circular, it's closed, and it only has 37 genes. Specifically, in those 37 genes, there are 2 rRNAs, there are 22 tRNAs as indicated in the green strands, and there's 13 polypeptides. Now, the nuclear genome has low gene density in that it only has 1 gene for every 40,000 base pairs. But in the mitochondrial DNA, it's densely packed in regards to genes because for each gene, there's 450 base pairs. Another piece of information that's not noted here is that mitochondrial DNA does not have introns. Nuclear DNA has introns. Moving on, we're going to be looking at the arrangement of genes in yeast in figure A versus the arrangement of genes in humans in figure B. You're going to see that there's genes and genome-wide repeats, and that there's less distance between each gene here, so it's condensely packed here, but it's not condensely packed in humans. Apparently there's a lot of these genome-wide repeats, which many people would call junk DNA, excessive DNA, non-coding DNA, and basically 98% of human DNA is non-coding, while 2% of the genetic material in yeast is non-coding. So that's shown here. The 2% is right here, and basically it's condensely packed with DNA here that can encode for a protein. If you guys don't know already, non-coding DNA is basically DNA that cannot make a protein, cannot encode for a protein. And that, so junk DNA, right, so commenting on it, I think that I don't think that 98% of our human DNA is considered junk. I think that, some of these non-coding DNA are introns, and those introns can be spliced and used for expression of gene expression. And so I think that there is some junk DNA, but I don't think that 98% of human DNA is junk. I think more than 2% of the human DNA has a purpose, and that maybe there is junk DNA in our bodies because people can delete certain genes in mice and still see no apparent damage. And I can probably assume that for human beings as well. Well, so this is basically just telling us that not all of the genetic sequence in DNA actually encode for a protein. And we can differentiate each species by the amount of junk DNA that they have. That's right. That's it.